Thank you. Good morning, everybody. Thank you for, well, I would like to thank the organizers for providing me the opportunity to present this work today. As Michel said, it's a joint work with Valérie Girardin from the Université de Caen-Normandie. Here I'm interested in measuring the information of sequences of random variables, and more precisely, I am interested in two problems. The first one is given some type of random sequence, stochastic process. Can I explicit the entropies that will be good information measures for these random sequences? And the second problem is some kind of dual version of the first one. That is to say, we fix some entropy functional and we seek for random sequences that for which the given entropy functional is a good information measure. So what I intend by good information measure is an extensive entropy functional, and I will explain in a few slides what is it exactly. So let's start with some basics. I think it is useless to take time for presenting Shannon entropy. You may also know some other entropy functionals, such as Renit, Salis, and so on. These entropies and many others are part of the family of the so-called H-phi entropy functionals, which are given here. And one of them that I will be interested at the end of my talk is Salis entropy, which depends on a parameter Q, which is given here. Okay, this is all these definitions hold for a single random variable, and when you are interested with a sequence of random variable, well, you may first consider the sequence of marginal entropies, that is the entropies of the n first marginals, or the n first coordinates of the sequence, and then make n tends to infinity. So when you're lucky, this sequence of marginal entropies grows linearly with the number of observations, and then renormalized by n, by the number of coordinates. Then it converges to some limit, which is called the entropy rate of the sequence, and it represents some average of per variable entropy. Okay. Of course, this entropy rate exists if and only if the sequence of marginal entropies grows linearly with the number of observations, and this property is exactly extensivity as Salis defined in its seminal book here. Okay, so heuristically it means that all variables contribute essentially in the same way to the total amount of information of the sequence. There is something that remains unclear in the definition of Salis. This is that extensivity is some kind of two-way relationship, some kind of compatibility relationship between an entropy and a random sequence. So we may say that an entropy is extensive for a random sequence if the focus is on the random sequence, or alternatively, the sequence is extensive for some given entropy. Okay. So, what is known about extensivity? Let's start with the basic situation of an independent and identically distributed sequence of random variables. Okay, so you may know that for Shannon entropy, well, Shannon entropy is axiomatically characterized by this property known as the strong additivity that says the entropy of a couple of random variables can be decomposed into the sum of the entropy of the first marginal and the conditional entropy of the second marginal with respect to, conditionally to the first one. Okay, and extensivity is derived from this assumption in the case of IID sequences and also for other ergodic sequences. It is strongly linked with the famous asymptotic equipartition property. Roughly speaking, essentially extensivity is some L1 version of the AEP. And so there are numerous theoretical and practical corollaries to the AEP. I give some instances here, but you probably know that very well. Okay, departed from this classical framework, what can we do exactly? What can we say about extensivity for any kind of sequences? Well, probably the main attention has been brought to ergodic sequences, but anyway, we can say, what can we say? If we want to adapt the proof that I sketched here, we need some axiomatic characterization of other entropy functionals, but it will be a tedious way because it's you will derive proofs in a one-to-one approach, okay, by considering each axiomatic property characterization. We did it some years ago in a GSI paper for Renyi entropy, but well, okay, it's quite tedious because of the well, it is attached to any for each entropy. So there is an alternative approach which is axiomatic free and much more powerful that originates from analytic combinatorics, and it consists in linking the behavior of the marginal entropies to the asymptotic behavior of the so-called Dirichlet series associated to the sequence. I will detail this in the following slide. And by this link, we are able to completely explicit the asymptotic behavior of marginal entropies for a large class of H-phi entropies. Okay, and we also derived some classification of H-phi entropies depending on this asymptotic behavior in a previous work. Okay, so I will detail briefly what is the Dirichlet series and what we can say about how can we use it for our purpose. Okay, so the Dirichlet series associated to a random sequence is defined for a given n and a parameter s as the sum of the probabilities of the outputs of the sequence, well, of the first n outputs of the sequence to the power s. Okay, it is an amazingly powerful tool for investigating the dynamics of the chain, because you can convert any kind of question on the dynamics of the chain, including entropy behaviors. You can convert these questions into functional analytic questions and classical ones, and so it's a very powerful tool. So in the following result, I will be interested in some kind of sequences, in a family of sequences, namely the quasi-power sequences. So here is a proper definition, but I may comment it instead of reading it. So it says essentially that the Dirichlet series of the sequence behaves as the power of some quantity plus some remainder that is neglectable with respect to this term. heuristically, you can see that result as an extension of the classical Perron-Frobenius theorem for stochastic matrices that says for under conditions on the matrix there exists a unique dominant eigenvalue associated eigenvector associated to the eigenvalue 1 from which you derived a lot of results. Okay, so for this kind of sequences, we can answer the first question, that is to say, can we explicit entropies that are extensive for this kind of sequence? And the answer is, on a large subclass of H-phi entropy, there are only 3 entropy functionals that are extensive for these QP sequences, namely Shannon entropy, Renyi entropy, and the logarithm of Taneja entropies. Okay, so now let's have a look at the second problem. You fix an entropy and you ask, is there any sequence for which this entropy is extensive? We will have, can I say, well, Turner and Hanel, who are physicists, has derived some heuristical results that link the growth of the state space of the chain with the entropy that you have to consider for being extensive for this process. Okay, for example, they say that if the state space grows exponentially fast with the number of variables, then Shannon entropy will be extensive for this kind of process. If the growth rate is polynomial, then Tsallis entropy is the good one to consider. Okay, these are heuristic results, and there is no actually processes that are highlighted in this work. And so we wanted to get something more explicit and that something that we could simulate. Okay. So here is the idea to get. So I will focus on Tsallis entropy only for the purpose of the talk, and I would like to be able to build some sequence for which Tsallis entropy is extensive. So the idea is to start with a classical random walk and to twist it enough to make it extensive for Tsallis entropy. And so we will act by relaxing the ID assumption in the RID assumption, so preserving independence but allowing for each increment of the random walk to be distributed in many fashions. So, okay, I recall some properties of the Dirichlet series, and probably the most important for us here is the last one, saying that when you are dealing with independent random variables, then the Dirichlet series is the product of the Dirichlet series of each component. And so the idea is that when you are dealing with independent increments for your random walk, then the Dirichlet series of the increments equals the product of the Dirichlet series of each increment. And so Shannon entropy, the Dirichlet series become exponential, so it satisfies the QP sequence. And for such a situation, the random walk is extensive for Shannon entropy. And the idea is to slow down the convergence by whether removing some factors in the product or changing the values of the product. So we have two levels of actions for tuning the behavior of this Dirichlet series. Whether we will introduce delays between random increments That is, you will move randomly for one move, then wait for a while before moving again randomly. This is the first level of action, and the second one is, well, tuning the distribution of each random increments for the product here to be as you want. That is, it increases linearly with the number of factors. Okay, and so we can. Okay, I give the toolbox here because I don't have any time anymore. But it is quite awful, so we'll comment it in a few words. So you have these two levels of action, but that will change the behavior of the Dirichlet series, and so the marginal entropies. But you want this Dirichlet series to grow linearly, so it makes some constraint on the actions that you can do. And actually, there is only one degree of freedom. That is to say, if you modify, if you introduce delays, then it will constrain the values of the factors, and conversely. So here, we present the result by saying, okay, we will fix the values of the Dirichlet series of each component. Okay, I give them, and then the random, the delays that we have to introduce for the Dirichlet series to become linear are these ones. Okay, so it works. I give some example here, but just anyway, you can simulate many types of behavior. Whether you can, well, you can have some random walks that are isotropic for in any dimension by acting on the delays. You can also have anisotropic random walks by exploring preferably some directions and so on. So okay, I will stop here. Thank you very much. Yeah, exactly. Well, yeah, it was one of the first idea I have explored actually, with the idea that we have the classical independence and we may have some Q-deformed independence, but it's quite difficult to formalize because what will be the interpretation of the distributions that you will make the Q product of something, but what does this mean? So it is not the marginal distributions of the couple, and so we didn't manage to give some intuitive sense to this kind of thing. So we tackle the problem by just not acting on independence, but on the other part. Okay.